It is.
Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth. Today we're joined again by Kevin Rusnick, the senior historian at the Air Force Research Laboratory. He's here to separate space fact from space fiction and tell us how the Air Force helped us get on the moon.
In 3, 2, 1.
Kevin, welcome.
It's good to be back. Thank you for having me again.
Absolutely. I think you now hold the record for we've had you the most on the podcast now.
Well, 2 isn't much of a record, but I'm proud of that anyway.
Still said it.
Yeah, I mean, when we get to SNL level, you'll be like our Steve Martin.
There you go.
You can look forward to it.
Eventually I'll be hosting it, right?
We'll flip it on us.
Yeah. So, Kevin, we're closing in on the 50th anniversary of the Apollo 11 moon landing, which happened on July 20th, 1969. A lot of what I know about the moon landing came from, high school history classes or the movies. And I don't know if that makes you cringe as a historian. What's your take on learning history through movies?
Well, to look at it from a positive perspective, anything that encourages people to learn some history is a good thing. Something that sparks your curiosity is great as far as I'm concerned. If that's all you're doing, though, is the only history you're getting is from what you see on TV or in a movie, well, then, it gets a little bit cringeworthy as a historian, because movie makers, even ones with the best of intentions, people who are trying to make a historically accurate movie without making a documentary, they have to cut corners, they have to combine characters, they have to compress events in order to tell a multi-year story with hundreds or thousands of characters in 2 hours in a way that's accessible to people. Yeah. So you realize that as a historian, these things happen. And so you can make a judgment call on whether they should have done this or done that or what they show. But as long as the history that is presented is fairly accurate or gets to the truth of the matter without necessarily being factually precise in everything, you have to appreciate that. And so I think with Apollo, at least recently anyway, the movies have done a fairly good job of that. And when I saw this question from you guys last night, it made me look up what are all the movies that have been shown about Apollo. And surprisingly, given the significance of it, there haven't really been that many, or at least ones that are that popular. And I'm looking at just fictional ones, or ones that aren't meant as documentaries, but are these kind of dramatic takes on the Apollo program. And of course, the most significant ones in recent years first was Apollo 13. That kind of revived interest in the Apollo program. It's probably been almost 20 years now, I guess, since that came out.
And that movie then, or even touching more recently with First Man, do a lot of people after they watch these films reach out to you to say, hey Kevin, how close are these to the real story? Or do you more reach out to other people saying, hey guys, come close, let me tell you?
Well, that's where social media comes in. Because when First Man being a great example, obviously there was no Twitter or Facebook when Apollo 13 came out. So it's the community of space enthusiasts and space historians was kind of walled off from the rest of the world. You might have some bulletin board, electronic bulletin boards, things like that, where you can communicate, some websites, things like that weren't all that widespread. But now, of course, you've got all the buildup from leading up to First Man since the book came out years ago, and then the various iterations of trying to get this movie made. The spaceflight history community has been very interested in this and followed every detail, every casting decision, every image that popped up online. It's been examined under a microscope. And so, after a while it kind of gets fatiguing, but then once the movie comes out, of course, there's a huge influx of interest from people that aren't just the real enthusiasts, but from other people as well. And then, that's when you get questions that are in the general category of how realistic is this, or what was that they showed, or what did they screw up? Honestly, the enthusiasts are the ones that tend to pick out all the details that are incorrect. And some of that you kind of want to roll your eyes at, the color of this dial was wrong, or he turned left instead of right, stuff like this, that in the bigger historical sense doesn't really have any significance. And you appreciate that enthusiasm because you want them to get all those details right. And if you talk to the guys that are making these movies, the producers, the prop masters, whatever, they really work hard. They use as much evidence as they can, photographs and things, to make stuff as realistic as possible. But ultimately, they do have time and budgetary constraints, and they're trying to make a movie.
Sure. Tell the story
Right.
in 90 minutes or 120, depending.
Exactly. And so, it's something like First Man, where they really try to adhere to the story, but in a historically accurate way. Again, as I said before, I really applaud those guys. That movie, though, had some really mixed reactions, though, because they try to take a unique perspective on it. They try to get into the psychological drama, as it were, of Neil Armstrong, to kind of get inside his head and tell the story of this Apollo 11 mission, the first moon landing, that we all know more or less. And how do you tell that in a unique and interesting way to engage a modern audience? If you just go from start to finish, hey, they trained for a mission, they flew the mission, they landed on the moon, they planted on the flag, they came back and had a ticker tape parade, well, that's kind of boring from a movie watching
It almost
perspective.
feels more like a documentary at that point, or maybe even just a featured story. So.
Right.
Yeah, there wasn't enough drama because there's a lot of stuff in his head and in his personal life, probably.
Yeah, I mean, looking at Apollo 13, like you mentioned, that was plenty of drama in that movie. So,
Yeah,
I mean,
right.
That's one that's made it fun.
Yeah, because it had this moment that made this dramatic turn in the mission. If the oxygen tank had never exploded on Apollo 13, they would have landed on the moon, collected rocks, and come home. Nobody would have ever made a movie about it. The name Jim Lovell would just be another of in that case, it would have been 14 astronauts that landed on the moon instead of 12, and that would have been that. But because there was this dramatic moment that literally made for TV, as it were, that mission became famous. So.
Yeah, they got Tom Hanks. I mean, it worked out.
Right.
Kind of going to maybe not quite the drama side, but more of an interesting side that people don't know. With the talk you've been doing more recently, kind of traveling about, talking on Apollo and its legacy, you've touched on the Air Force's impact on the program, and many people may not know how much they've done for it. So could you kind of explain what relationship the Air Force and NASA had, and kind of what helped make the Apollo 11 mission happen?
Apollo, being the pinnacle of human spaceflight at the time, built on this tremendous technological and organizational base that had been set through the Gemini program, the Mercury program, and then going back to the Air Force and other parts of the military. It wouldn't have been possible if the military hadn't done all of these other things related to space flight, and even before that to aviation. If you want to think of space flight as kind of the next step beyond flying higher and faster, right? And so who's pioneering that? Well, of course, there's the Navy too, but we work for the Air Force Research Laboratory, so I'll talk about the Air Force some. Like any history, you can take it back as far as you want. You can go back to McCook Field or whatever, but it's the Air Force's interest in flying higher and faster in order to survive, in order to get a mission accomplished. So if you want to have your aircraft fly over enemy air defenses, well, you go faster. You fly higher than the enemy can fly their airplanes or shoot you down with ground-based guns or missiles, whatever it might be. And the faster you go, you can outrace people. And so the Air Force, particularly after World War II, once the jet engine is developed, we get into this realm of what we think of as aerospace. We're getting into not just tens of thousands of feet, but maybe 80, 90, 100,000 feet for aircraft. So we're getting just kind of on the edge of space. So what kind of technologies are involved there? And so the 1950s and early 1960s, you see this kind of watershed change in terms of how we're designing aircraft. You get things like swept wings, the jet engine, as I mentioned. You have special alloys for building the surfaces of aircraft, because aluminum is going to melt when you go Mach 3, because the friction of the air moving around your airplane heats up the skin. So we get into high temperature research for metals. We get into composite materials, ceramics, these kinds of novel materials that NASA's later able to leverage. You look at different kinds of propulsion. I mentioned jet engines. Of course, Apollo's not using a jet engine, but it uses a rocket. The Air Force didn't invent rockets. You've got people in Germany and Russia, and of course Robert Goddard here in the United States, who becomes kind of the father of American rocketry. But we adopt it pretty early on, and here at Wright Field, we're looking at small rocket engines as early as the mid-1930s.
Oh, wow.
Yeah, and in fact, Robert Goddard had been working since really around World War I, and the guys in McCook Field were aware of the rocketry research that he was doing, and we even sent somebody a few years later out to check out what he was doing. And there's a famous line that I like to quote. I think I put it in their book that after looking at Goddard's research, the guy came back, a young Lieutenant Sessoms, who later becomes a general in the Air Force, concluded that Dr. Goddard's rockets appear to have little military value. So, which in retrospect seems funny, but at the time, it of course, he was right, because it was a very experimental kind of novel technology. But as that technology matures, we look at what we can do with this. So not only looking at like a rocket-propelled weapon, what you think of as an aerial rocket that you use to attack a ground target or maybe to shoot down another airplane in a small missile kind of sense, but as a propulsion device for an airplane. And that's really our first application here for the Air Force is what happens if we strap some of these small rockets onto the side of aircraft for what they call jet-assisted takeoff.
Yeah, and that was, you said, that testing was more taking place during World War II, or is that when they kind of really said we could really use this and push it?
Yeah, and that's where you see this first application. In the United States, of course, is lagging far behind Germany, who, the V2 rocket by Werner von Braun and his rocket team, that's of course, the epitome of rocket development at that time. And we're just using these small rockets, again, for aerial weapons or for, helping bombers take off with heavier loads in a shorter distance. But that work's being done here. We had here at Wright Field.
Which is crazy now because we're like 5 miles from a downtown, like very urban area. And
yeah, and in fact, they still were at that time. It was, the test stands were actually not that far from where we're sitting right now. They were testing, we had a rocket testing complex over there, and they just got rid of the last buildings maybe 15 years ago or so.
Oh, wow.
But you're exactly right. You've got the point after World War II, once we have all this captured German technology, particularly the V2s, we quickly realized that the test stands we have here are entirely inadequate for the future of rocketry. We need something bigger, we need a safer place to test these things, because not only is it noisy, but if it blows up, bad things happen. You've got all these other buildings around. Even if we're on an enclosed base, you've got all these other laboratory buildings and so forth. So that's when we look at a new place to test and how we end up out at Edwards, and we move our rocket testing facility out to what they call the Rock or the Rocket Lab. It has a whole bunch of names, but that's where we still do our rocket testing today. Our Edwards facility, the RQ West, as they call it, the Aerospace Systems Directorate.
California, more desert landscape, a lot more space, less populated.
Yeah, I was trying to imagine just the sound you'd hear, because even hearing some flights nearby Dayton, you can still hear some aircraft, but hearing rockets testing, I can only imagine.
Yeah, it's of course a tremendous amount of noise. So once we move the testing facilities out there, we're able to build a complex where any of the rocket contractors can test their large rocket engines there under with safety and security, because it's a closed facility, so you don't have to worry about the danger to the population, but it's also a place where you don't have to worry about espionage or something like that. And those facilities have grown tremendously over the years, and we'll talk about that in a minute, particularly because of the Apollo program. But to get back to the link to the Apollo program, we're developing these rockets. The Navy's developing some, we're developing some. We're looking mainly at solid rockets early on, but liquid rocketry becomes another emphasis of ours. And one of the guys we think of as the father of solid rockets, that is ones that have a propellant that, if you kind of look at it, is maybe like something like clay or toothpaste almost. It's a mixture of fuel and oxidizer all together, so that way you just set it on fire and it burns, right? This is great because you can store it essentially forever, for years, and you can launch it right away, so it's perfect for a weapon. Liquid rockets can have a lot more power, a lot more thrust, if you will, but you got to fill them up and you have to launch them essentially right away. But it's a technology that because of the Germans mainly, we become more familiar with early on. And so you look at our first missiles that we use for what we call IRBMs, intermediate range ballistic missiles, and later ICBMs, the intercontinental ballistic missiles, the ones that can go all the way across the ocean. Those are all based on this liquid rocket technology. We're using a fuel, mostly kerosene, we call RP1, rocket propellant 1, and liquid oxygen. You mix those together, you burn it, and boom, there goes your rocket, right?
Yeah.
So the Air Force is developing these for rockets that can go longer and longer ranges, hundreds of miles and eventually thousands of miles. We're developing those to power aircraft. You see one, for instance, that powers the X-1, the research airplane that takes Chuck Yeager past the sound barrier. So we're looking at all these different applications for rockets. Well, our rocket lab was headquartered here. Even after we moved the testing facility out to Edwards, all of the research and development activity was still going on here at Wright Field. It was part of what was called the power plant laboratory, and then later on they called it the propulsion laboratory. But until 1959, all of the science and technology, those guys were still here. We'd go out to Edwards to do the testing, but that research was going on in this location.
And was there any contained testing here then, like a much smaller scale, or literally?
Yeah, we continue to do some smaller scale ones for like aircraft rockets and things, but basically anything of any size really went out to Edwards. I think they ran their first test in 1952, as I recall, out there. And then it just got bigger and bigger, and we built bigger and bigger test stands to accommodate for it. So it's this sponsorship of rocket research and the S&T we did to support rocket development and to build up the rocket industry that NASA was able to leverage when it was formed in 1958 to put a man in space.
Yeah, so I'm sure at that point they had no doubt in their mind, like, we need these rockets, we just need all this to come together to get the right material to space.
Right. And of course NASA was formed out of several different agencies. The kind of core of it was the old NACA, the National Advisory Committee for Aeronautics, which, as the name implies, they were mainly focused on aeronautical research and a few other things. Their facilities in Langley, they had engine research up in Cleveland, a place out in California, but then they were also given the Wernher von Braun group, the Redstone Arsenal, the rocket researchers that had come over from Germany that were in Huntsville, Alabama. They became the NASA's propulsion experts. So they were the ones that started what we think of as the Saturn family of rockets, the one that got us to the moon. But interestingly, and this is the critical Air Force connection. If you think of the Saturn V, that's of course the giant rocket that put men on the moon, right? This 363-foot tall multi-stage rocket that goes up there. If you guys have ever seen one, there's a couple of them still around in museums. The one I've seen the most is parked out front at the Johnson Space Center in Houston. I mean, you can't really fathom the size of this thing until you stand up by it. But the first stage has these 5 massive engines that are taller than any of us. The engine bells, where the fire comes out, the business end of it, right? I mean, they're wider around than like this table. I mean, it's huge. But that rocket is called that rocket engine, the 5 of these is called the F1. It was built by a company called Rocketry. Well, what does this have to do with the Air Force? And the Air Force actually started that engine. We were looking in the mid-1950s at where could we take rocket technology? The first ICBMs were on the drawing board. We were looking at things like the Atlas missile. But each engine, I think the state of the art at the time was around, 300,000 pounds of thrust. I think the highest one actually in production was about half that, about 150,000 pounds of thrust. So 300,000, that sounds like a lot. And it was, but again, we're talking drawing board sort of things. Well, guys here, and the Rocketry guys, remember specifically, the propulsion researchers here asked them, well, how big do we think we can go? What's the maximum we can take kind of current technology and scale it up? Because scaling up an engine isn't just as easy as, okay, well, we need twice as much thrust, so we'll just make everything twice as big, right? Yeah. Engineering doesn't work that way. So we asked that question as well, how big can we make this? So we could get together with Rocketry to study this. They decide, well, okay, we're looking at about 300,000 pounds. Let's try 1 million pounds. Okay, or
just jump for 1 million.
Yeah, okay, a million sounds good. We can't imagine right now what we're going to do with 1 million pounds of thrust on a single rocket, but you never know. We're looking at, hey, each rocket's gotten this much more powerful, so eventually we'll figure out something for it. You build it and they will come kind of mentality, right? Yeah. So we think, okay, 1 million, this is great. Well, what about 1.5 million? Okay, well, sure, let's go study that. So we pay Rocketdyne to start designing this. They take their existing rocket technology and they think, okay, well, how can we simplify this and increase the size and thrust at the same time? And so they start what we know as the F1 engine program. Well, when NASA gets stood up to put man in space and eventually go to the moon, they end up taking over that program. So the Air Force gets out of it and NASA takes it over, and that's what becomes the first stage of the Saturn V rocket. It, in fact, develops 1.5 million pounds of thrust per engine. So you stick 5 of these on the first stage, so you end up with a first stage rocket that's 7.5 million pounds of thrust. I mean, this is an insane amount, but that's what you need to put a guy on the moon in the most kind of efficient manner possible.
And just to kind of set it for people, you mentioned how large these are. Do you know the actual, like the full length of these rockets?
The dimensions I don't know offhand, I'm sorry, but they're big.
Yeah, the important part is they're huge.
Yeah.
And so you're kind of making that connection now with the Air Force and NASA's program, but after the Apollo program started, how much did the Air Force work with NASA during that time? Or was this more, like you mentioned, technology we passed on and consulted with?
So the most direct connection, and the most active connection, I should say, during the 1960s, during the NASA's manned space flight era, or kind of the golden era, if you want to think of it, was through what we think of as aerospace medicine. Jumping back to the Wright Field era, you have Harry Armstrong comes here to Wright Field and really founds this discipline of aeromedical research. They're the guys that look at, hey, how can we help people survive in this kind of higher and faster environment, survive at high altitudes? And because the lab he founds here, which we'll call the Aeromed Lab or the Aeromedical Research Lab, it changes names, but we think of it as the Aeromed Lab in general, so I'll use that term even though it doesn't really apply for the full period we're talking about, but for simplicity's sake. So they're the guys that look at the first development of high altitude pressure suits in the Air Force. So if we're flying at altitudes where there's not enough oxygen and pressure to survive, or for a person to survive, well, let's wrap them in a suit to do that. So that research really kicks off during World War II, and it really grows from there. Even after the war, we're looking at various types of pressure suits, both in an experimental sense and in a very practical sense, because we're flying bombers at, again, say maybe 50,000 feet, where if they lose cabin pressure, then the person's not going to live, right? So you need a pressure suit as an emergency device. So say you lose cabin pressure, then this pressure suit will inflate, or some of them, what they call mechanical counter pressure suits, will actually squeeze your skin to provide with the mechanical pressure against there to keep your blood, the air in your blood from boiling out, causing the bends, which if you're a scuba diver, you know about that kind of thing.
Sounds like a terrible thing to be the person to help test.
Yeah, well, I've got stories about that too. But so we come up with these pressure suits to help our pilots with that, and we test them in altitude chambers here. We do all this development. We build up the contractor base that NASA then leverages to build its spacesuits. I mean, you think of all kinds of things as spacesuits, but honestly, there aren't that many true spacesuits. Everything is what you think of as, most of what you think of are these actual pressure suits. They're not really intended for doing a spacewalk or walking on the moon or something like that. But the technologies, the basic technologies are very much the same. You have some kind of bladder, to use the term, that contains pressure. So usually basically some variant of a rubber bag, and then some layer on top of that to keep it from stretching out of shape. If you think about a balloon when you have it, well, a balloon, it may look like a kind of like a sphere or a sausage or something. And then once you inflate it, what happens? Once you start putting air into it, what happens? It stretches out. Same thing would happen to a pressure suit if it doesn't have a restraint layer on the outside of it to keep it in shape.
So a lot of these are meant for more training then for a lot of the astronauts, or you said they just use this for the stepping stone?
Right now we're talking about for Air Force pilots flying airplanes. Okay. So what we're developing this technology, this know-how to do that. And so we're the contractors that are building suits for us. Once NASA comes along, they're like, okay, well, Mercury program, we're going to put one guy in space. Okay, he's going to be in a pressurized cabin, but what happens if it springs a leak when he gets in space? We don't want to kill an astronaut just because, you know, there was a hole or a micrometeorite or something punches a hole in there. So he needs something like these Air Force guys are using. He needs a pressure suit that can inflate and keep him alive long enough to get back to Earth. So they look at the existing state of the art, and in fact, this is an activity that was done right here, literally a couple hundred yards from where we're sitting right now. They asked the Air Force to evaluate the existing pressure suits to see which one would be the best for use in the Mercury program. Because as I mentioned, the Navy was doing this as well. So there was a Navy suit, and then there were a couple of Air Force suits. So we did all these mobility tests. There's pictures of guys, you know, they're putting their arms like a clock at different angles to see how they can stretch and reach and operate different controls with this pressurized. Because like a balloon, once something's inflated, it becomes more rigid. So it's not very easy to bend when you're in an inflated pressure suit. So mobility was really a key factor here, both inflated and how comfortable it is when it's not inflated. So we do this evaluation for NASA, and we recommend, hey, this Air Force suit that we've been using, that's the one you should use, it's great. NASA, their crew systems division head, he's the guy that's responsible for suits, says, well, thanks, but I'm from the Navy, I like the Navy suit better, so we'll use that one. But anyway, but we did that evaluation here, and
also probably some testing.
Oh yeah, quite a bit of testing, in fact. We would test these in the vacuum chambers. As I said, we do all this mobility testing and so forth. And then what ended up happening, because of the allure of the space program, putting men in space, you see a lot of the guys here, the engineers that worked here, they think, hey, cool, I want to go work on the manned space program. So a lot of our technical experts left here and went to what became the Johnson Space Center. Then it was the Manned Spacecraft Center in Houston. So there was that knowledge transfer by the physical transfer of people going there. And so you see the same experts that were developing pressure suits here go work for NASA, develop the first pressure suits and the first space suits for them. And same thing happens on the Gemini program. That one uses basically a modified Air Force suit for that, the one that kind of lost out from Mercury. But the Ed White, the guys that did the first American spacewalk, those suits are based on Air Force technology. Once they get to the Apollo program, they use this tremendous knowledge base they have to essentially clean sheet design a suit, but they're using these principles developed first by the Air Force and the Navy, and then on the Mercury and Gemini, particularly thinking about joints, like how do you move your arm or your neck or whatever it is in a spacesuit to design the Apollo lunar suits. And so if we hadn't done that work, though, NASA wouldn't have had that knowledge to leverage, and it would have taken them much, much longer to get it done.
That makes sense, yeah. With how much, it's a lot of, people don't really consider how much goes into not only getting to the moon, but even building the spacesuit or getting the rocket set, or like you mentioned, transferring knowledge with people.
Right.
So that just goes to show even just a few major parts of how much the Air Force has helped influence the program. Mm-hmm. But tackling more into Apollo 11 then, with the crew itself, can you kind of go into maybe some of the training they may have gone through, or kind of what it meant to be an astronaut at that time to get ready for the moon? Anything
you can imagine that you would need to do in space, they did to the nth degree, from geological training, traveling to different places around the world to learn the basics of being a geologist, looking at rocks. You go out to the desert and try to figure out how to identify what might be significant. I mean, if you think about that, these guys are going to the moon, a place where nobody's ever been. I mean, we've sent probes, we've taken pictures, we understand more or less what is going to be there or what we expect to be there. But when you have a guy actually walking around and he's surrounded by rocks, well, okay, he can just grab a bunch of random rocks and some dirt, throw it in a bag and bring it back, and that's something that's never been done before, great. But you want to make sure that these guys are able to do this to the best of their ability, as well as a professionally trained geologist would. You want them to be able to identify what are the most significant rocks around them, what's something unusual. Because if you grab 10 bags worth of dirt and rocks that are all the same, well, you're going to learn a lot about those particular samples, but you want to get a variety. You want to really get a sense of the history of the moon, the geology that's there, and you can't do that unless you've been trained to do that. So they would spend hours and hours doing basic geological training. Of course, some of the astronauts took it more seriously than others, and where you see this training really pay off is in the later missions where they actually stay on the lunar surface for more than a few hours, when they stay for days and they have the lunar rover to drive around to different areas and collect different rocks, and you see that pay off. But when you're talking Apollo 11, Neil Armstrong and Buzz Aldrin, they're only there for a couple of hours, so they literally are doing, hey, let's grab some samples, and get them back, and anything beyond that is gravy, right?
And where did they go to actually train them? Like you said, they traveled around.
Some of it was in Arizona, Hawaii. I think later ones went to, I think it was Iceland. These places where
cool.
you think
where really
volcanic, because they're expecting the moon to have a lot of volcanic activity.
Yeah.
So that's where you would send the guys to areas where you would see volcanic environments, so they could identify that kind of rock. And of course, the moon did have some of that, but it wasn't all of that. A lot of the craters and things were made from impacts, so it's you get that kind of those rock formations based on having been hit by meteors, things like that. So.
And did they, as the crew, they've spoken a lot about their mission well after the fact. Now that we're celebrating the 50th anniversary, have they mentioned maybe like something indispensable they did, or saying a part of training they say is absolutely the most important, or something that really stuck out to them?
I'm not sure I've heard them discuss and kind of in retrospect the key bits of training, but having talked to a lot of the engineers and flight controllers, these people, I think from in my opinion, the most valuable training they did was in the Mission Control Center.
Okay.
So thinking about the activities they have to do while they're going to the moon, launch and re-entry as they're going. So where they're running through all the different procedures, running through malfunctions and things, all the interaction they're having to do with the ground. And so this kind of simulation, they did probably thousands of hours. You'd have the guy sitting in the Mission Control Center, you'd have the guy sitting in the simulator for the command module or the lunar module, and they would run through the procedures for landing. And then you would have a simulation group, these simulation supervisors or sim soups, throwing different errors at them. Okay, there's a problem, boom, something went wrong, okay, how do we fix that? They would learn all these procedures. And so that way, when something went wrong, and things did go wrong, they would know how to respond to that right away, and they could solve these problems.
Yeah, no panic, just right after it.
Yeah, and Apollo 11's the great example. As they're landing, they get this computer alarm, this 1201 alarm, where the computer is basically getting overloaded because of a radar issue, and it pops up, and oh my gosh, this is the first landing on the moon. If they hadn't trained for this exact scenario, they might have panicked and aborted and didn't land on the moon. Well, because they knew what to expect, the flight controllers, they recognize what's going on, they know what's happening. They're able to tell the guys, hey, it's all good, just we'll bypass that alarm for now. As long as these other things don't happen, you're all well and good.
Yeah, because that could be alarming, right? Yeah. Saying that like, we'll be fine, let's just push that aside.
Right, so I think that kind of training is something that NASA had been doing since the Mercury program, really, and then continues to do for the Space Shuttle program now, because you don't want to be in space and not know what to do. And of course, Apollo 13, another great example, where their training does pay off, but that's something you could never have anticipated. Blowing up an oxygen tank would have been unthinkable for a simulation for the most part, just because it causes so many things to go wrong. But because they had trained in all these other areas, they could leverage that training to do enough workarounds that they could contain the situation and come up with solutions to get those guys back alive.
Yeah, and touching on what you mentioned too, a lot of these areas, they have to be in constant communication with mission control.
Right.
How powerful were these communication devices they were using? Because going from the moon to Earth at that time sounded extraordinary, and still does, honestly.
Yeah, we had a network of communication stations around the Earth. Australia is one of the great examples, where essentially the Earth always had one of these antennas pointed out in space, and it's actually easier to communicate. You need fewer of these stations to communicate with people going to the moon than it is circling around the Earth, because they're always, when you think about the line of sight, they're always in a different position, so you would have to have so many different stations to follow their orbital track. But as you're going out to the moon, as you're looking at the moon, it's seems more or less stationary, but it's going across the night sky, but as the Earth is rotating, you've got a much wider field of view toward the moon, so you need fewer of these stations. And so yeah, you need a relatively big and powerful antenna to get the signals there and back, but it's actually not as bad as you might think for that kind of thing. But yeah, we were able to be essentially in constant contact with those guys as they went.
And something that we were talking about before this, we were kind of touching on with this being the 50th anniversary, kind of what Apollo 11 means to not only the United States, but the world and its legacy.
Right.
So during your talk, is there anything you touch on talking about how it's impacted our culture and kind of how it's really painted our worldview today?
There's the classic saying, right, that well, if we can go to the moon, why can't we do X, Y, and Z? It's still seen as perhaps the greatest technological achievement, certainly of the 20th century, if not, ever. It's this thing that hundreds of years from now, when we've long forgotten about, who was president a particular year, World War I and II, it's another, go into the history books as, just another war like all these other ones that you guys vaguely remember something about from history class. But we're always going to remember that we stepped foot on a different body other than Earth for the first time. This guy, Neil Armstrong, maybe they won't remember his name offhand, but the fact that we did this back then is something that's going to essentially live forever for hundreds or thousands of years, as long as we have history. And so that is such a significant event by itself. I mean, just the fact that we've done that. And I mean, the symbolism there is, hey, we managed to do this achievement in an era that was fraught with turmoil. You're thinking about all the social change going on in the 1960s, the Vietnam War, civil rights, all of these things, and we were able to do this tremendous technological feat that kind of was symbolic of almost an earlier era where, hey, we can leverage technology to do almost anything we want. And then after Apollo ended in 1972, we had kind of come back down to earth by that point. It's like, well, we don't have unlimited amounts of money to throw at these great technology things. We're doing these tremendous feats, may not get us where we want to go, as a society. Sure, they're inspirational, but hey, we have other priorities. We need to do these other things. But it still stands as a tremendous achievement, not only for the nation, but for the world. And we tried to give it that symbolism as at the time. If you look at the plaque left on the lunar lander on Apollo 11, it says, "Here, men from the planet Earth." It doesn't say, "Here, men from the United States." They were trying to represent everybody.
Absolutely.
And that's one of these other great legacies is you were able to see, because of the space program, the moon landing program, you're able to look back at the Earth and see the Earth as a whole. You can see this blue sphere kind of hanging in the middle of a whole lot of black nothingness. And this is what the Apollo astronauts, at least the more philosophically inclined ones, talk about. When you're looking at the moon or looking at the Earth on the way to the moon, what do you see? You don't see borders, you don't see the wars going on, you just see everybody together on one planet. And so that really gave them a perspective that, hey, we are all in this together, and there's nothing else out there as far as we can see, so we really need to take care of the planet that we're on and kind of take care of each other. So
that's a truly inspirational message.
Yeah.
That's powerful. Yeah, that's one thing I've definitely seen a lot of people talking about, that blue marble hanging in space, kind of how beautiful, fragile, but powerful it looks.
Right.
So, and I can't even imagine going up in space and seeing that for the first time. That'd be amazing. And something we kind of want to throw in here at the end to kind of have a nice tie is there any fun facts about the Apollo 11 mission that many people may not know that you like telling them, or during your talk you brought up?
Fun facts. Well, it wasn't filmed in a studio by Stanley Kubrick. Is that a fun fact?
That we're finally going to expose it this time.
Yeah. No. It's as a historian, you try not to get too wrapped up in fun facts, but it's always I usually more interested in kind of debunking these sort of myths that get wrapped up around it. Like, hey, we spent however many millions of dollars to develop a space pen when the Russians used a pencil. And actually, I'm holding one of these space pens as we speak, right? No, the Fisher Company developed this pen on their own and sold it to NASA because it would work in space. But we use grease pencils. The Soviets used pens as well, so it wasn't one thing or the other. So those kinds of things aren't really true. I don't know. The whole mission was fun to me. I mean, it was really cool stuff. But one thing I did want to point out, as we're talking 50 years now, Buzz Aldrin. If you guys know his full name, Edwin E. Aldrin Jr. Well, Edwin E. Aldrin Sr. was an Air Force officer or an Army Air Corps guy. Where was he 50 years before his son landed on the moon? Right here. He was in the first class of what's now the Air Force Institute of Technology at McCook Field.
Wow.
Yeah.
That's a lot of people don't know that. I sure did.
Right. So if you look at kind of the first graduating class, 1919, the AFIT was the Air Service Engineering School, I think was the name of it at the time, set up by our buddy Thurman Bain. Edwin Aldrin Sr. was in that particular group. So you can go see his picture, and then 50 years later, his son's landing on the moon. And of course, Buzz was also a graduate of AFIT, as were many of the Apollo astronauts. So
well, that's great. Seeing
that's
the legacy.
Kind of a cool tie-in.
Yeah, 100 years and 50 right there, him and his father.
Right.
That's really cool. Well, I don't know if you had any final questions for Kevin.
No, I think that's it. Kevin, thank you for your time again.
You're welcome.
Thank you so much for joining us. This has been great.
Yeah, it's always fun, and I mean, there are lots of other Air Force things to tie in, so I don't want to give all the other guys, like our materials researchers or the electronics guys or anything like that, the short shrift, but in the time we have, it's impossible to talk about everything. So
yeah, we can talk about space food and
yeah, of course.
zippers on spacesuits another time. So.
Right. Lots and lots of that stuff.
Thanks.
Thanks, guys.
And to keep up to date with future and past podcasts and to check us out on social media, make sure to see us on Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And make sure to stay curious.
Logging off.